Hi, good evening. This is Glenn Newell from the San Jose Astronomy Association, and welcome to the first of my online live workshops for astroimaging. We're normally out at Little Uvis Open Space Preserve. You can see a picture of it here, and I kind of miss my horse buddies and whatnot. And we normally start just at sunset, and I give a lecture on usually all overview of different types of astroimaging, and then go into a demo once it's dark enough to see Polaris and get polar aligned and all of that kind of stuff. But tonight is going to be a different presentation. I'm going to focus specifically on deep space astroimaging, which is near and dear to my heart, and we'll talk about what deep space astroimaging is and what's in store for tonight in a few slides. But first, also, we have Rashi is from SJAA is going to help me watch the YouTube for questions, and a little later on, Bruce, who runs the imaging special interest group, will also be joining, and he's going to be helping me demo some equipment and software and whatnot after we're done with the slides. So let me go to but first, here's a little blurb about SJAA. Let me get my camera out of the way here. In this presentation, I've tried to include, whoops, switched off the wrong thing there. Tried to include QR codes wherever there's URLs so you can point your smartphone and click rather than trying to write down URLs that aren't clickable in the YouTube stream. So, um, San Jose Astronomical Association, SJAA, we have two main ways to see what's going on with us. One is the sjaa.net website, and then the other one is we use meetup.com/sj-astronomy is where all our public-facing events are scheduled. And you probably know that because that's how you RSVP'd for this. But you'll see there that we're a super active club with lots of things going on, which include, here's on the left is what our website looks like, and there's tabs with resources across the top, and then on the right we have the meetup. And new this month, due to the whole COVID thing, we're starting to have a lot of online content. So there's 4 different YouTube channels at the moment. We'll work on maybe consolidating things, but my personal channel is where I've been posting pre-COVID stuff. So that's the first one here, and that goes back to the days when I was just starting the hobby with DSLRs uh, and smaller scopes and all that sort of stuff. And then there's the general SJA website, I'm sorry, YouTube channel, um, where you'll find this presentation when it's over and additional things that I've helped with the streaming on. And then we've got a couple other sites of the Cosmos channel where um, basically the intro to the night sky and sights of the cosmos talks are going to be held. And then Solar Sunday has its own channel at the moment too. So those are the live online channels. So SJA does a ton of stuff. We're a nonprofit organization, and let me click on my small camera here. Get the mouse on the right screen. Okay. So we do in-town star parties at Hoagie Park in San Jose. We have a quick start program to help people get started in the hobby and find out if they're interested and what they're interested in before they go and spend money. We have a telescope loaner program, which also helps with that same type of thing. We do school star parties, and we also have monthly speakers right after our board meeting at Hoagie Park, and those are now online as well. Click. Uh, Intro to the Night Sky classes. We have a library on site at Hoagie Park with astro books, including astroimaging. Besides my program, which is more hands-on imaging, we also have the imaging special interest groups, which meets roughly on third Tuesdays of the month, where we have speakers regarding astroimaging and/or group discussions and share techniques and whatnot. This is the astroimaging workshops and field clinics part is what I do. And then okay, I think just a second. I think I need to do something here to let Bruce into the meet. Yes, admit. Hey, Bruce.
Hey, how you doing, Glenn?
Okay, I was just doing the SJAA commercial slides, so I'm gonna jump back into that.
Oh, okay.
All right,
Sorry to interrupt.
no worries. Thanks for joining.
Yeah, I'm gonna duck out actually, just stay connected, but I'm gonna take care of my connections on the other end here.
Okay,
All
thanks,
right.
Bruce. No worries. Yeah.
Okay.
Okay, and going on with the SJA activities, we partner with the Open Space Authority to get access to some of their great sites for nighttime activities. For instance, my events without COVID being involved are at Little Uvis OSP, as I mentioned. And then we have dark site star parties at Rancho Canada de Oro, which is one of their open space sites. We do have swap meets a couple times a year, which is fun. Good way to buy and sell astro gear. We have solar observing once a month on Sunday at Hoagie Park. That same Sunday, we have fix-it sessions. If you've got a problem with your scope, you can come in and get advice or get help to get it fixed. And then the club does a number of for members, not for the general public. We have private viewing slash imaging from dark sites from the OSP and uh, other places. And all of this you get for just $20 a year. So it's a great deal, I think. So let's move on. And clicked a few too many times here. All right, tonight's agenda. So as I mentioned, uh, normally I do a lecture that covers kind of all aspects of nighttime sky photography, which might be nightscapes, star trails, time lapse, or somewhat, wider fields of the sky. And it's a lot of material to cover, and I've covered it a bunch of times, and it's available online. So tonight, I want to focus on specifically on deep sky astrophotography. And as part of that, I wanted to start by talking a little bit about light pollution and how we can deal with that because it's a ever growing problem. I want to talk about what do I mean when I talk about deep space, and I want to talk about the hobby challenges and then the solutions that we can help bring to be successful in your hobby. And we'll go into a little bit deeper on rig design and try not to get too deep in the weeds, but it's a little hard to avoid, but we'll see how we do. And then we'll talk about the hardware that Bruce and I will be using tonight, and we'll talk about the software stack or the combination of software that Bruce and I will be using tonight. They're different, just as our rigs are different. And then we'll do a live demo of actually, taking some astro images. And as part of that, I'll be also demoing some live stacking, which you might do if you wanted to share astro imaging with an audience in a quicker way than your typical long exposure astrophotography, which is what we normally do for deep space. And there'll be a couple other things thrown in along the journey here, but let's get started. So light pollution. So I live in Union City, which, is a suburb of the San Francisco Bay Area, right here where this pin is, and this is what's known as a white zone, which is the worst light pollution uh, on the scale, right? It's pretty bad. Uh, and so how do we deal with that? And being I choose to image from here because I can have a semi-permanent setup and image from my office in the house and image while I sleep and all that good stuff. And my rig's too big to really haul around anyway. But I choose to do that despite all this light pollution. And so how do we deal with that? So there's a couple things. Let's start with narrowband filters. So before LEDs, unfortunately, LEDs are broadband, but before LEDs, man-made light tended to be in very discrete bands of light, sodium vapor, mercury vapor, neon, etc. And so it was easy to make light pollution filters, which I'll show in a minute, which sort of notch out a lot of that stuff. But now we have LED lights, which are broad spectrum, and hopefully they'll meet their design goals of pointing down at the ground and not so much up at the sky and not lighting more than they need to. But coming back here to narrowband filters, so I uh, generally like to image nebulae and that can be done with narrowband filters. And so that's where filters are just notched out to cover these narrow bands of light that are emitted by emission nebulas and to some extent reflection nebulas. So these bands of light are called hydrogen alpha, singly ionized sodium, which is called S2, and doubly ionized oxygen, which is called O3. And then there's one or two objects that are hydrogen beta, but for the most part, imagers use just these three bands. And then the lighter colors here are what your RGB red, green, and blue filters would look like, and they try to put these notches, or at least this one here, where some of that sodium vapor, mercury vapor stuff might be. Although you'll see that oxygen 3 is sort of smack in between your red and your blue filters. So we use these again for these false color images that you see. The Hubble palette is the iconic name for that. Although there's lots of variations of what you can do to make artsy colors. Um, and so you take, a monochrome camera with these filters, and then you assign them red, green, or blue in any combination that looks good to you. I wanted to bring in, if we overlay this, here's what a light pollution filter might look like. So this is if you're got a color camera, for instance, and you're not getting, because you have a color camera, you're not going to be doing narrowband, and we'll talk about that in a little bit. But you could use a light pollution filter, which again is trying to notch out some bands where you might have undesirable light versus light from the sky, which is again these tend to be these nebula bands. Okay. Um, I was just glancing at the YouTube there. Don't see any questions yet. Feel free to chime in with questions. The other thing that you can do from light pollution is be patient and collect lots of data. So yes, it's not going to be, you go to a dark site and image for 45 minutes and come away with some data that you're going to then process. That's not going to happen from a light pollution area, but you can get the same end results by just increasing the total exposure time. So my rule of thumb now for here in Union City is 10 hours of integration per filter. I try to get to that point before I even try to process anything. And yes, that might be like 45 minutes or an hour or something equivalent from a dark site. But again, the upside for me is with automation. I can sleep while my rig does the work, and so patience does pay off. So just as an example here, here's one of my images. So this is the Eagle Nebula M15, and it contains, if you look closely right here in the center, you might recognize the pillars of creation, which is a famous Hubble shot. In fact, let's take a look. So there's the Hubble shot right there next to mine. And, not too shabby if I do say so myself. If you blow this up, of course, the Hubble is much more detailed because the Hubble doesn't have to deal with the scene in the atmosphere, which we'll talk a lot about tonight. So it's crystal sharp, and also, it's got a 2.4 meter mirror, and I've got a 12-inch mirror. So anyway, but I can't operate the Hubble from my office, but I can operate my rig. So all right. So what do we mean by deep space when we talk about astroimaging? So what we mean is galaxies and nebulae for the most part, and I guess I should include globular clusters. Um, so those are deep space objects versus, say, Milky Way shots or some of the bigger nebulae. Even I wouldn't put in this category. I would call it wide field, like the North American Nebula or the California Nebula, or some of the H2 regions um, are bigger. Some of the dark nebulas are bigger, but galaxies and bright emission and reflection nebulae are what we mean by deep space. Uh, Unfortunately, in terms of the overall hobby of nighttime photography, it's going to be the most expensive. It's going to be the most complex. It's going to be the most mechanically sensitive, and we'll kind of hit this point again and again. And that kind of drives what makes it so fiddly, right? And because of all those things interacting, there's lots of failure points, uh, and so you just deal. So multiple software and hardware working together. We typically have some planetarium software, mount driver software, autofocus, image capture, plate solver, auto guiding, and then we want to automate all of the above so we can do things like meridian flips and multiple targets and image all night. Um, so as a couple examples here of galaxies and nebulae, these are both taken from a robotic scope in Siding Springs, Australia, that's pictured on the underneath my camera here. Let me turn that off for a minute. And so on the left, we have the Helix Nebula, which is one of the, to me, most amazing objects in the sky because it looks just like a human eye with an eyelid and everything. It's kind of spooky, but there it is. So also called God's Eyes Nebula. And that's a false color image in the Hubble palette. You'll see it in a lot of different a lot of different colors arrangement, but this is the one that I did. And then on the right, this is a southern hemisphere galaxy, Centaurus A, and that's an example of LRGB. So again, a monochrome camera, but with luminance red, green, and blue filters versus the God's Eye Nebula, which was done in narrowband hydrogen alpha, sulfur 2, and oxygen 3 filters. Okay, let me cover my footnote here. I can turn my camera back on. So the footnote, there we go. The footnote says if you hold a golf ball 9 kilometers away from your eye, it covers an arc second of sky. Okay, so keep that in mind as we go through the slides here, and I'll explain why that's important and what an arc second is and all of that. But that's really driving what makes this hobby so fiddly, is that arc second. Okay. Um, So to go a little bit more into the challenge of deep space astrophotography, right? So up here on the left, we sort of have the minimalist, put a camera on a telescope and call it good. And don't get me wrong, you can start that way, and there are people that get very excellent images with not much more equipment than just that. We have Francesco, excellent imager, one of the best image processors I've seen. He uses a DSLR and a small refractor and an intervalometer and a mount and a standalone auto guider, and that's about it. And uh, but that's most when I talk about deep space astrophotography as a hobby, what most people are doing is more like this bottom picture here, right? So they're hanging a lot of gear on their mounts and they're automating everything. And what that ends up being is, you're sort of a Jack or Jill of all trades, right? So you're an amateur astronomer. You need patience and perseverance because all this stuff has to work, together. You need to know a little bit about optics. You need to know a little bit about mechanics. You need to know a little bit about electronics. You've got to use computers and software. If you're also into do-it-yourself stuff, you can go nuts with 3D printing and Arduino, sorry, projects and similar. And then there's also some artistry involved when you get into the image processing. So for me, as a Silicon Valley engineer, it's kind of like the perfect storm of a lot of different things that I like to do. So that's where I got sucked into the hobby. So those are the challenges, but you know what? We're here to help, right? So SJA is here to help. So we've got a community of astro imagers that hang out on a mailing list slash Google group that's for club members. We do have the Fix It session I mentioned before. We have workshops and SIG meetings, and then we're starting to have these online resources. And then we've got there's a typo here. It's supposed to say field clinics, private imaging, observing for club members only, right? So you can go hang with your club buddies at a dark-ish site. And do imaging and help each other out. And that's typically what happens is you learn from each other and help each other out at these private events. Okay. All right. Let me move my camera out of the way again. So why not just camera and telescope? What is the reason that you need to go more complex than that? Well, first of all, your terrestrial camera or daytime photography camera is going to be a color camera, which means it's got what's called a Bayer matrix of filters in front of the sensor. So every 4 pixels has one red, one blue, and two green filters in front of those 4 pixels, and that limits what you can do. It makes it difficult to do narrowband because there's already color filters in the way. Um, and another issue with daytime cameras is that they typically have a large part of the IR filtered out. And all of this has to do, why are there 2 green pixels and why is the IR filtered out? And all that has to do with trying to match the camera sensors to the color reproduction of the human eye. But if you think about, when we're trying to do deep space astrophotography, we've already sort of abandoned the human eye as not the effective tool, and so we're trying to see things like hydrogen alpha, which is pushed into the IR part of the spectrum that gets filtered out by these terrestrial cameras. Also, certainly with the new mirrorless cameras, the camera companies have made a decision to put them in the market without so much of the ability to control them remotely with computers. It's not a technical challenge, it's something they decided to do to position them in the market versus a more expensive DSLR. Now, there are newer softwares that have sort of back-ended or reverse engineered or figured that out. But for the most part, the commercial astroimaging programs aren't going to work with mirrorless cameras, even though those are very excellent cameras in terms of taking pictures of the night sky. Uh, Good news is we can build those same sensors from those cameras into dedicated astro cameras, but I'm getting ahead of myself a little bit here. So the next thing is, these cameras are not cooled, and cooling makes a huge difference in the amount of noise that you see when you take images of the sky at night. Um, there's something like a doubling of noise for every 5 degrees centigrade of temperature that you can cool the sensor to. So typically, you're going to run your dedicated astro camera at -15, -20, or sometimes even down to -40 uh, degrees below ambient temperature, and that makes a big difference in the amount of noise in your image. The other thing that I would note is, when you buy a terrestrial camera, every year there's more and more megapixels, and it's supposed to be better. Well, it's better for, you know, daytime imaging, and now you can do 4K or even 6K video with these things. But none of that really helps with nighttime photography of the sky, because what's really limiting your resolution is the roiling of the atmosphere. If you look up at the moon, it sort of fades in and out of focus, or royals, and that's an example of what's called the seeing, and we'll talk more about that. Um, but there are some mitigations, for some of these restrictions that I just talked about, right? So there are, for color cameras, there are 2 or 3 different manufacturers doing either tri-band or dual band filters that are sort of like super light pollution filters that try to cut down and just show you uh, the bands again of the nebulae, but it's going to be a little bit different because of the oxygen 3 being right between green and blue. They can't split that out into another color like you would with a narrowband and monochrome camera. But they do have that. And then back in the day, when CCD cameras were very expensive and all there was in terms of dedicated astro, some people did take DSLRs and modify them, and one of the modifications was to chemically remove that Bayer matrix. And a lot of cameras got ruined, and you often had sensors with some dead rows or something, but you could do that. I had a Nikon that I bought that somebody had modified like that and used it for several years. And then, there's IR modifications where some the IR filter is removed completely and either replaced with a lesser strict IR filter or optical glass, and exactly what IR modification is done to the camera kind of affects both its nighttime performance and whether or not it can still be used for daytime and do things like autofocus and stuff. And I mentioned that, some of the newer software does work with mirrorless cameras, but in the beginning, the mirrorless cameras just weren't going to work. And then, of course, there's do-it-yourself cooling projects. So you could build a cooler for your DSLR to cool it down. I messed around with that in the beginning. I had both a water-cooled Canon and a water-cooled Nikon on my rig at one point. And then, of course, you could cool electronically as well. And if you're going to go with DSLRs, I advise people, don't worry about modifying your DSLR you just spent, seven, $8,000 on, 700 or 800 or $1,000 on. Keep that for daytime use, and because of this scene effect, a Canon T3 or a Canon T3i or a Nikon D50-100, those older cameras are all you need, and you can buy those already astro modified, with this IR modification all day long for 300 or 400 bucks on eBay or what have you. Um, just check the shutter count. Other than that, you should be good to go. But then the big reason why not to do that is today, now we have cooled CMOS astro cameras. So people have taken these same CMOS sensors that were designed for DSLRs, and they're making them into, they're buying them without the Bayer matrix manufactured in place, and they're making them or with, if in the case of one-shot color, but for deep space, for me, monochrome cameras, and they make them into these cooled astro cameras. You can see the heat sink here, and there's a fan on the back that does the cooling, and all the camera electronics and the sensor are up in this front part here. And they're relatively inexpensive compared to CCD astro cameras of the past. Okay. The other thing, that's driving just a camera and a small refractor on an inexpensive tracking mount is, working towards improved tracking. So the stars appear to move in the sky because the Earth rotates. Um, Pop myself back on here. And so we need to track the stars or the objects across the sky. And, it takes good mechanics to do that accurately. That's getting back to that arc second accuracy again, which we'll hit again and again. So better mounts and sky models are a reason for that. Improved tracking and auto guiding is gonna um, help you get that much more accurate. So auto guiding, the mechanics of the mount are going to track at a certain rate, and that's it. But so there's going to be some inaccuracies due to gears and dirt and in the grease and whatnot in your mount. But with auto guiding, you can correct for that by having typically a second camera and potentially a second, even a separate telescope uh, connected to your mount. Like, see right here, this guy's got uh, a guiding scope on top of his main telescope. So he's got a guiding camera and an imaging camera. So the auto guider will look at a star and just focus on that one star and see how it appears to move relative to the camera frame, and it'll send corrections to the mount to speed up or slow down to keep that uh, perfectly centered. Back in the days, astronomers used to ride up in the cage of their the big telescopes, and with a joystick, manually with their eye glued to a finder scope, and manually keeping the star on the crosshair. So today we have auto guiding software to do that for us. Also autofocus. So, with this rig up here, I mentioned, you could get focused with the aid of a batten off mask or something at the beginning of the night, and you'd be good to go for a while. But what happens is the temperature changes as things cool off, and so that means things shrink, and so that actually changes your focus point. And so you would have to keep focusing periodically over the night, so you'd have to go slew away from your object to a bright star and refocus and then slew back to your target or what have you. But with autofocus, that all goes away and it's managed for you and can be adjusted. You can either figure out what your focus varies with temperature and just have it take care of that for you, or you could say, I want to autofocus every few minutes or every so many degrees of temperature change or with every filter or change or what have you. Um, so that's just part of this whole automation that we'll talk about next here, right? So we want to automate everything so that we can do things like, uh, all night imaging. So when I first started in this hobby, again, DSLR, uh, great DSLR control program, Backyard EOS or Backyard Nikon, I could track an object across the sky up to the meridian, which is the zenith. If you draw a line, the high point in the sky, and then I'd have to shut things down unless I wanted to stay up and manually do that meridian flip to come back around through Polaris and back the other way. And that has to do with German equatorial mounts, which I don't really cover in this talk, but all of the astro imaging mounts, or let's say 95% of them are German equatorial mounts. They can't cross the meridian directly. They have to go back through Polaris and come at it from the other side to avoid banging the camera. If you've got a long refractor, banging the camera into the mount leg or something. So if you're going to sleep through that meridian flip, you need a bunch of automation, right? Because you need to, stop tracking, turn off the auto guider, do the meridian flip, come back around, get back on your target, turn the auto guiding back on. Maybe check the autofocus because you had mirror flop or something. So all of that, doing a meridian flip is a complicated operation that can be done with automation. Also, multiple targets, right? So you might want to do 4 or 5 targets during a night, and you can do that with automation all while you sleep. This is a picture of my current rig, or some of my current rig anyway, uh, here on the right, and we'll talk more about that. But this is a 12-inch uh, Ritchie Christian reflector, and like I said, we'll talk more. All right, so we're going to try to not go too deep in the weeds here, but we're going to talk a little bit about designing a deep space astro imaging system. So first point that I always make to people is, okay, and it looks like my stream is hung. There we go. Come on. All
Yeah, I just
right.
started back up again.
Okay. Not sure how much time did we
Just
lose? Just a
maybe
second.
about 2 to 3 seconds. That's it.
Okay. All right. Oh, I must have neighbors streaming Netflix or something. Okay. So I was saying the first point that I want to make about an astroimaging system, well, you're probably thinking, oh, well, what telescope and what camera, but that's really not the first thing you want to think about. The most important thing is the mount. It's all about the mount. And this is where we come back to this. You need this arc second accuracy, right? So if you need something that's as accurate as the width of a golf ball 9 kilometers away from you, you can imagine that that's not going to be, uh, cheap commodity hardware, right? It's going to be a precision piece of engineering. Um, and again, we'll keep hitting that. So that's uh, the most important thing. And there's sort of a rough rule of thumb, if your overall budget you think you're going to spend on this hobby is less than say 10K, then you're probably going to want to spend about 70% of your budget on the mount. If you're going to spend more than 10K, and people do, then maybe it's like 50% on the mount. But the mount should be the first thing you pick and the most important thing, because your hobby is going to be so much easier and so much enjoyable if you're not fighting the mount to get good tracking and to get round stars, to get good guiding. It's just so much more enjoyable with a quality mount. The other thing that I think tends to happen is you buy a small beginner mount and it may be okay for your small beginner telescope, but then when you want to upgrade, you not only are going to be upgrading your telescope, but you're also going to have to upgrade the mount because the payload, it might be accurate enough, but the payload capacity isn't going to be enough as you move up. So, buying a mount once instead of buying it again and again, is another strategy. And then, you know, the different manufacturers. I'm not trying to single out Orion here or anything, but we have Orion is here local to us in this part of California, and so I have a lot of experience with the different Orion slash Skywatcher slash Cinta mounts, which are all OEM versions of the same thing. The Atlas Pro. Is really the minimum mount that I would recommend, and there's the capacity and some of the upgrades that mount has, the belt drive, the saddle, the extra thick counterweight, et cetera, that you would have to add to a lesser mount, make it a good package deal. And so, but spending or think about spending around $2,000 on a mount as a minimum. Okay, click.
Glenn, I just want to quickly interject.
Yeah.
Some people want to do like very wide field deep sky,
Hmm.
and there are less expensive options if you're doing a DSLR with a camera lens at this point. And that's a good way to start actually for a lot of people. So you might want to talk about that to start adventure. Okay.
Yeah, again, thanks, Bruce. This talk is mainly on the deep space stuff, and we'll talk about fields of view and stuff in a little bit here. But yeah, certainly for a DSLR and a small refractor, or like Bruce said, a camera lens, there are less expensive ways to go, which make it very portable and lightweight. Even no counterweights maybe. But again, that's limited with what you can do, in terms of when you start to do galaxies and nebulae. Okay, so let's move on to the telescope. So there's kind of two schools of thought. One school of thought is, hey, this hobby is hard enough. Let's not start with a super long focal length that's going to be fiddly. Let's start with a small, inexpensive refractor and have a wider field, or even like Bruce was saying, a camera lens. Get you started in the hobby and see if you enjoy it or not before you go bigger. So that's one school of thought, and that's the advice that I got when I started, which I didn't take, and I jumped right into RCs. But to each his own. And so then I'd say the second uh, school of thought is, go big or go home. So, if I'm going to do this thing, I'm going to go all the way, right? So design for the maximum performance. Again, depending on what your goal is in terms of objects. Um, and so, aperture is king. And the biggest aperture bang for the buck is going to be some type of reflector. And the most popular ones for imaging are either RCs or SCTs. Now we can talk about the variations of those and imaging Newtonians and whatnot, but for my money, uh, RCs are the biggest bang for the buck, and then SCTs are quite popular as well. Um, that said, big refractors are less fiddly in terms of something called collimation, keeping all the optical components aligned. They're easier to operate and maintain, but they do cost more uh, for the most part. And they make beautiful images with no diffraction spikes. If you don't like diffraction spikes, then you get a big refractor. Um, So Bruce, this is actually a picture of Bruce. Let me put my mouse on the right screen so you can see it here. This is actually a picture of Bruce's rig, which one of Bruce's rigs, which is a pretty much the biggest amateur refractor, right? Is a 152-inch triplet. Yeah, so that's an amazing scope. Okay, and then there's also one other flavor that we can talk about that's becoming kind of popular, and it's pretty new actually. It's a variation on the Starzona Hyperstar modified SCTs, which is the Celestron Raza. Bruce, what does that stand for again? Roy? Is it Roe Ackerman Schmidt something astrograph?
Roe Ackerman Schmidt astrograph.
Hey, I
Correct.
I eventually fumbled my way around to that. Okay,
That's
great.
correct.
Yeah. And this is you'll see the cameras on the front of this thing, which causes its own set of problems, right? You can't have a big filter wheel there. You got, if you, how are you going to get your wires in and out of there without causing diffraction spikes you don't like or something, So there's it's so my thing is it's like a race car, right? It's extremely high performance, but it's also very fiddly, right? Very precise spacing and alignment and all of that stuff to get that performance out of it. Um, might be, is, I should say, a good, if you're going to do one shot color, that's an awesome scope. And they come in 8 and 11 inches, but uh, if you're going to do narrowband, right, then you're going to be manually changing filters and there's some more stuff. But if you want to get the maximum amount of data in the shortest amount of time, there is that option these days, right, Bruce? Bruce has an 11-inch Rasa too.
Yes,
Okay.
that's correct.
All right. So this is where we go probably a little deeper in the weeds than this lecture probably should, but it's important, right? So matching and OTA stands for optical t- uh, telescope assembly, I believe. I knew that earlier today.
Optical tube assembly.
Yeah, optical
Optical
tube
tube assembly.
assembly. Okay, yeah, I knew that earlier today and had since forgotten it. But yeah, because people just say OTA all the time. So matching your telescope and camera. So we have to talk about some concepts here to get the right terminology. So everybody knows there's 360 degrees in a circle, but did you know there's 60 arc minutes in a degree? And did you know there's 60 arc seconds in an arc minute? So there's that dreaded arc second thing again that we know we need to be accurate to an arc second. So it's a 60th of an arc minute, which is a 60th of a degree. Okay, and we're going to use those terms to define things like field of view and arc seconds per pixel in our camera. And those are terms that we're going to use again to match camera and optical tube assembly together. Okay, and going back to the visual side for a minute, just to kind of get you oriented again on sizes of things in the sky, right? So this is a cool chart, often used, right? So if you hold your fist up at arm's length, it covers about a 10-degree space of the sky, right? So then we can go down to 1 degree with your pinky finger, and then from there we're off into the arc minutes and arc seconds. And remember, we said the arc second is a golf ball 9 kilometers out. And I've got another analogy for that as well. So when we come to then the field of view, this is means, what is your telescope going to be able to see on the sky? Um, so you kind of need to know, well, what is it? What are the sizes of things on the sky, not in terms of light years width or something, but because, how they are on the sky depends on how far away they are, how close they are, not just on how big they are, right? So we're going to talk about the field of view of your telescope. And so the way I like to think about it are, again, focusing on deep space. There's a few wide field objects out there, right? And you think about Andromeda, the big nebula, like the Rosette, I mentioned before, the North American Nebula, the California Nebula, and some of the H2 regions and stuff are pretty big. So there's tens of those. As you go around the Milky Way, you can count. Maybe there's 20 or something. I don't know. Um, so there's a few of those, but most galaxies and bright nebulae are, in tens of arc minutes. They're not degrees across, they're tens of arc minutes across. And then there's even smaller objects that you might want to image, planetary nebula, and, smaller galaxies, further away galaxies tend to be less than, say, 6 arc minutes across. So, it's hard to say what people have, but I'd say your typical deep space field of view might be 30 to 60 arc minutes across. So here's a couple examples. So, on the wider side, this is kind of an iconic framing of M81 and M82, right? So you get two galaxies in one frame, and you're going to need about 60 arc minutes. This is 55 and change by 42 and change arc minutes field of view here, as shown in Stellarium against a image of M81 and M82 by Rob File, one of our SJAA members. Uh, so that's a typical size. And then here we have on the smaller end of things another kind of iconic image of the Horsehead Nebula, and try to do this from memory. NGC 2023 maybe, one of my favorite nebulae there. Um, but this is 31 and a half by 24, say arc minutes, right? So somewhere between those two is what you're typically going to want to shoot for to get most deep space objects without having to do uh, mosaics or frames, multiple frames of these to put together a picture. All right. Um, So then comes the more technical stuff, again, getting down to this arc second per pixel. I just want to bounce back for a minute here. Okay. So again, we talked about on the surface of the Earth, as opposed to like the Hubble Space Telescope, seeing this roiling of the atmosphere limits our resolution. And seeing is measured in arc seconds. And typical amateur seeing, and by that we mean, down on the ground or maybe a mountaintop, but not a carefully planned observatory site, right? Observatory sites are very carefully planned. not just to be high up in the air, but to have this lamellar, pronounce that right, flow, smooth air flowing over the observatory site, um, so as to have less of that roiling air. So they have better seeing than we do typically. But for amateurs, it's typically around 2 arc minutes. That's a typo. It should say 2 arc seconds. So therefore, using sampling theory, the what you need to do to get that maximum resolution in a photo would be to have 1 arc second per pixel. So 1 pixel on your camera would see 1 arc second of sky. And so we go back to, after a certain point, more pixels don't help because you can't get any finer resolution because of the scene. So there's a couple things that you can do about that because what happens is modern sensors have more and more pixels as the pixels get smaller and smaller, and it becomes actually difficult with the modern CMOS cameras to have even you're always going to be oversampling. You're going to have, like half an arc second per pixel or zero point 0.4 or zero point 0.3 or something. So one of the things that astrophotographers typically do for deep space is they add a focal reducer, which can help you get back more towards this 1 arc second per pixel rule of thumb. Right, so it's going to lower the focal ratio. It's going to widen your field of view, but it will eat back focus, and back focus is where I drew the line on this being beyond the scope of this particular lecture. But basically, it just means that you're going to run out of inward travel on your focuser, and you can't come to focus uh, if you're trying to get too much focal reduction with the focal reducer. Okay. I already talked about the pixels are really small these days. And so there's a number of ways to calculate both the field of view and the arc seconds per pixel. So I've posted the formulas here on the slide, but that's the hard way. So there's lots of, Stellarium as a planetarium program can do this. There's lots of web pages and other online facilities, calculators that can do these calculations for you. There is an excuse me. There's an older program called CCD Calc that's really nice, and it also has like Stellarium. It'll show you the images. Of your target, what they look like in a field of view. There's a one of the telescope simulator sites, I forget which one. There's probably more than one does a similar thing. So you can try out different combinations of stuff there, and we'll talk about another way in a minute. And then the other point I want to make here when considering cameras and stuff is sensor size really drives the cost, and it does so for like 3 or 4 reasons, right? So you can get a great astrocam, and I'm referring here to the ZWO ASI 1600 as a super popular uh, astro camera, for about $1,300. But if you go up to a crop sensor or all the way up to a full frame, a 35 millimeter diagonal astro camera, you're going to be paying 4K and up for something like that. So just the cost of the camera, goes up as you increase sensor size. But there's some other, effects that happen too. So you need bigger filters, right? So you might get away with a 1 1/4 inch or maybe 31 millimeter filter for that 4/3 inch sensor, but for a crop sensor or a full frame sensor, you might need a 50 millimeter filter. So you can see just as one example for a particular And there's another typo. 5 nanometer HA 1.25 inch is 460 bucks. This was supposed to say 5 nanometer. Oh, I see. 50 millimeters, this should say. Uh, yeah, got it. 5 nanometers, 1.25 inch filter. This is 5 nanometers, 50 millimeters for that full frame sensor. You jump from $460 to $725, but wait, you need 6 or 7 filters to cover, the RGB and the narrowband and everything. So that can really multiply the cost of your rig. And of course, you need a telescope that's going to produce an image circle at prime focus that is what we call flat to that same width, right? So it's one thing to make a telescope that makes a small image circle that's flat, but it's more uh, difficult and costly to produce, a bigger flat image circle. So you're going to spend more on the OTA. You're going to need a larger focuser. If you're using a focal reducer, you're going to need a larger focal reducer flattener, and you're going to need larger filters. So all of those things are driven by the size of the sensor. So that's something to keep in mind. Now, of course, the flip side is you get a huge field of view, and it means you can image more without doing mosaics or what have you. But okay. So another way to look at field of view and actually just, what Astro gear works together and what can I do with it is to use AstroBin. So AstroBin is a great resource. It's very mildly sort of the Facebook or let's say social media for imagers because you post their image there and then people can like it or, you know, unlike it or and make comments, whatever. But what makes it a super great resource in my view is you can search for types of equipment, right? So here you see I've searched for a Canon T3i, right? So it's giving me all images that were taken with a camera with a Canon T3i. So you could search, what if I bought this RC and an ASI 1600? What can I do with that? And what if I had a focal reducer or didn't have a focal reducer? So then you can search and see what people are doing, and to also uh, you know they have this technical card that tells you more details. Well, what filters did they use? How many exposures did they take? How long were they? Did they cool? What temperature did they cool to? And all that stuff. You can, what was the arc seconds per pixel? All of that information is available here on Astrobin. So that's a great resource. On the right is an older view of my page. Um, but that's a great resource to figure out what to buy. Okay. Um, did I jump past? I did. Okay. Let me pop my camera back on here. All right. So again, tonight we're going to be using a couple different rigs. My rig here in Union City is this 12-inch RC truss. Again, the RC is the same optical design as the Hubble Space Telescope. It's um, the optical design that is used by most modern observatory telescopes, although they may have segmented mirrors or whatnot, but in general, they're this Ritchie Crichton design, optical design. Um, so that's the telescope, and it's sort of semi-permanent. I don't have a pier set in concrete, but I have a big pier set on a concrete pad. So that's my semi-permanent setup for astrophotography. And there's underneath the cover here on the pier. There's a local computer and a Wi-Fi rig and power supply and whatnot. So I can operate that from the house via Wi-Fi. Okay. And if we zoom in a little bit here, I'll call this the instrument package, right? And I started calling it that because I actually have a small refractor that I can take, this whole section off and put it on the small refractor and do wider field stuff. But this is my instrument package. So, there's a focuser here, and then I have do-it-yourself made that into a rotator with 3D printed parts and stuff. So you can see this belt here and this 3D printed gear is part of the rotator. So this whole instrument package can rotate around so to rotate the field of view on the sky. Okay, and then we have the focuser and the focuser motor for electronically focusing. And buried in here between the focuser and the rest of this is a focal reducer. Most of it's down inside the focuser. Then we have something called an on-axis guider. So you may have heard of off-axis guider. This is an on-axis guider. So basically what it is what's called a cold mirror at a 45-degree angle. And the reason it's called a cold mirror is the cooler wavelengths of light, namely visible light, come in here and bounce off that 45-degree mirror and go up through the filter wheel to the imaging camera. But the infrared, the hotter light, goes through the cold mirror and out here to another camera, to my guiding camera out the back. And that lets us do some interesting things like real-time autofocus continually, and also you have a image circle for your guide scope that's the same size as your image circle for your imaging camera, for your guide camera, as for your imaging camera. And that way you don't have to worry about finding guide stars, which is something that you might have to do if you have an off-axis guider. Okay, and we just have a different camera angle here, again showing the some of the rotator stuff and the electronics for the rotator, filter wheel, and imaging camera. Okay, Bruce's rig, again, that 152 millimeter stellar view refractor, and his is a portable rig. And in the bucket down here at the bottom, he's got a computer and a Wi-Fi router. And then his instrument package is pretty similar to mine, as it turns out. He has a commercial focuser and rotator combination, a Moonlight Nightcrawler, um, and then he's got the same focal reducer and the same onag, and it looks like ZWO filter wheel, and it's probably a ASI something ZWO camera on there. And then he has the guide camera on the back of the onag. So that's a very similar instrument package to what I'm running.
So Glenn, I do have a quick question for you,
Yep.
if you don't mind.
Yeah.
The rotator that you have for the entire package, do
hmm
you rotate to in between shots of the same object that you're taking, or is it only when you want to rotate the entire field of view and then take X number of shots
It's for framing the field of view per object.
per object? Got
Yeah.
it.
So it's not. So there's another type. You remember I talked about German equatorial mounts
Yes.
are 95% of the imaging mounts. Well, you can use um, alt azimuth mounts for
Mm-hmm.
imaging, but they suffer from something called field rotation. So
Yep.
the image appears to rotate as it moves across the sky. And there's another type of rotator called a camera rotator that you can use to correct for that. And that's not what this rotator is for.
Got it.
This rotator is to uh, arrange the rectangular field of view correctly for framing, artistically framing the object
The object.
on the sky. So
Got
before
it.
that, I would if I wanted to image multiple targets, I'd have to go out there and manually rotate things, and I'd be running back and forth from the house to the telescope,
Mm-hmm.
move it 5 degrees. Now, oh, you went too far, move it back 3 degrees, right? And the other thing that happens is with an on-axis or an off-axis guider, as opposed to a separate guide scope and camera, when you rotate that package, you'd manually you'd have to recalibrate your auto guider because you've now rotated how it relates to the mount and everything, right? The camera has
Mm-hmm.
has moved against the sky and the mount model and all that. But with a electronic rotator, it can keep track of and report, hey, I've now rotated 30 degrees, and PhD2, the auto guiding software, will see that and compensate for it so you don't have to uh, recalibrate. So that was a big
Got it.
motivator for me to build a rotator.
Awesome. Thank you, Glenn.
Yep. Okay, let's move on, and we're getting close, folks. We're getting close to the to the demo. So hang with me a little bit further here. So let's talk about the software side of things for a minute. So these days, there are lots of choices. In fact, it's an embarrassment of riches, I guess you would say. It seems like there's just so many things I can't like try them all and see which one is best. It used to be in my worldview, it was backyard Nikon and backyard EOS for DSLRs and Sequence Generator Pro for everything else. And there were more, but those were the big ones, right? But now, you've first of all, you've got multiple platforms, right? You've got Raspberry Pis. Some people image with their smartphones or tablets. You've got always had Windows. People want to use Macs. There's Linux. So there's all these different platforms now. And, now there's free and open source or commercial software for doing all this stuff. And what's going to, drive some of those choices are going to be, are you going to do the DSLR or mirrorless camera versus a dedicated astro camera? And what is the level of automation that you're going to try to achieve? Or did you just want to image up to the meridian and then stop? Or are you going to, uh, you know, stay up all night and do things manually? Or are you going to sleep and let it do its automated thing? And then there's also the choice of, point solutions versus all-in-one type of thing, right? So do you want to buy one program that's going to do it all, or even a free, open source program that's going to do it all, or do you need individual programs that are really super good at just their one or two or three tasks? So just some of the examples, right? So in the free open source category, also multi-platform, we have K-Stars, which actually has K-Stars slash Ecos slash Indie, has a bunch of names, but that's, it's an all-in-one, runs on all platforms, open source, uh, runs on a Raspberry Pi. So those are uh, you can even buy it as an appliance that is going to run from your smartphone, right? ASI Air or Stellar Mate would be examples of Raspberry Pis that come with K-Stars pre-installed. So that's one approach. Um, I mentioned the backyard EOS and Nikon. And there's another popular one called APT, and that's the one that I think that has sort of reversed engineered the mirrorless cameras. I don't have any firsthand experience with that, but when I tell people that mirrorless cameras can't be used, they tell me that APT can do it. So great. And then sort of the more traditional, lots of automation. Examples would be, sequence generator I mentioned, which I'll be demoing tonight. There's a newcomer open source Nina that's very popular. Bruce is going to be for the first time, I think, using Voyager tonight. And then there's kind of an oldie but a goodie, right? So the professional observatories, the itelescope.net and Telescope Live and other things that are built to be remotely operated are probably running Maxim DL and ACP. Um, so, but that's a high dollar item compared to some of these other things, but has more, possibly more capabilities. But there's many, many more. So that's just an example. So what do these things do, right? So I just made this up today, right? I had another deck that had, 6 Fs. Well, this one has five five Fs in it. So, we're going to find objects in the sky. So we're going to use a planetarium program. We're going to use a mount driver to interface with the mount's internal model of the sky. Or one could argue that that's all in the mount driver. But anyway, that's there. And in some cases, plate solve, which is going to help us more accurately get on a target versus just what the mount's go-to accuracy is going to be, regardless of how well or poorly we polar aligned, etc. Mount leveling on and on. Okay. We're going to follow objects, right? So we're going to use the auto guider for that. And as I mentioned, that improves and works with the mount driver to more accurately track the objects as they move across the night sky. We're going to focus on objects. So we talked about autofocus, or electronically, at a minimum, electronically focus versus run out to the telescope and manually turn a knob. We're going to control filters. So you're either going to be doing LRGB or just RGB, or narrowband, which is the HAS2 and O3 filters. So you have to, manage all of that. And then for the fifth F, I came up with film objects, which is, you got to make sequences of exposures and filters to put this all together, right? So how many of how long exposures and of what filter, are going to make my target image. So those are the things that this software stack needs to do for you. Okay. So what I'm going to be showing you tonight in terms of the software stack is I'm going to be using Stellarium, which is a free planetarium program. I'm going to be using EQMod, which is a free mount driver for those Orion, Skywatcher, Cinta, OEM flavors of mount. Um, and I'll be using Push Here Dummy version 2 is the auto guider software. Okay, PhD2 is how people usually say it. And I'm also going to be doing focus lock, although I will demonstrate SGP doing autofocus. But focus lock is how, using that ONAG device, how I continuously real-time focus all through the night, and even during imaging, it's adjusting the focus. Okay, and then I'll be using sequence generator to do everything else. Uh, and I will, on top of that, I'll be showing some live stacking. This was something we put together to do the visual Star Party online flavor of our events. And so this was a way of getting a color image up on the screen in a hurry, even though we've got monochrome cameras with filters. So we'll talk about that. And I've only found one piece of software that does that. It's called Astro Toaster. It's free, and it works with another piece of free software called Deep Sky Stacker. So I'll show that as well. And then Bruce will be using Voyager for the first time. Go Bruce. He's got a software bisque mount, so he'll be using the SkyX, which does a bunch of stuff. He'll be using it as his planetarium, as his mount driver, and for doing the plate solving. and he'll be using PhD2 like I do for auto guiding, and he'll be using Voyager, which is a commercial program that's fairly new, and it is supposed to be completely bulletproof. The guy that writes this software is a professional software engineer in the banking industry, so he knows how to write software that has to work no matter what. So that's his what he brings to the party here. So Bruce is going to be checking that out. And then we're going to just throw in one or two other items here. So I'm just going to talk about Stellarium for a minute at the beginning, because it's so much more than just the way I've been using it up until recently as a planetarium to find targets in the sky and move my telescope. There's so much more that you can do. It's really a planetarium like you would go to a planetarium and see a show. It's that level of tool, and it's free and it's multi-platform. So I'm going to spend a few minutes talking about that and also just compare and contrast, how you would use that as a visual observer versus how you would use that as an astrophotographer. So maybe, 10 minutes on that, and then we'll dive in. uh, so I'll go through kind of the whole setting up and imaging via, my gear and software stack, and then we'll take a look at some live stacking, uh, and then we'll switch over to Bruce, and he'll kind of do the same types of things with the software that we just talked about for his rig. All right. Yeah. Any other questions? Rob says he recognized one of his images. Yeah, it was his M81 and M82. That's one of the things that I've done with Stellarium. And if you download Stellarium and you download the user guide and you look at Chapter 8, you'll see my name because I wrote Chapter 8. And Chapter 8, or part of Chapter 8 is about putting your own images into Stellarium, or maybe there's an image you love off of Astrobin that's not yours, but you really love it. And so how to put those images in Stellarium accurately on the sky so that all the stars line up. And when you go to look at, well, what does M81 and M82 look like in my field of view in Stellarium, you'll get, Rob's image should you choose, or your own. So anyway, I did that a while ago, and that comes with Python scripts and stuff to make that happen. But then recently, I've started curating a list of SJAA Astroimager photos and putting them in Stellarium. So far, we've got 68 deep sky objects in there, and I'll probably keep growing that. So it's just kind of fun to go in Stellarium and see somebody their image in there in that planetarium program. Uh, so, yep. All right. So let's dive into it here. Okay, so that's going to come later. Let me get out of the PowerPoint and go to Stellarium. Okay, so this was the way I set up Stellarium for last night's armchair star party. And actually, another thing I want to mention about Stellarium is I've also added landscapes. Uh, so, for instance, SJAA has a number of places where we typically have star parties and private viewing events. So, for instance, here's uh, the sidewalk at Hoagie Park in San Jose. Uh, and that sidewalk points north, and this is where they do the in-town star parties. So there's a landscape for that, right? And then, we were looking at RCDO a minute ago, and what do we have? Coyote Valley. So this is where I used to do my workshops, and now we do the binocular events from Coyote Valley Open Space Preserve. So you can see the horizon lines and where you have hills in the way or what have you, right? And I'll just do maybe anyway. Little Uvis is here. Here's Mendoza Ranch. Is another place that we do private viewing from down in Morgan Hill. Right. So these landscapes, have utility besides just being kind of fun. In that, uh, I think where was it? Well, you can see there's big trees and stuff that might get in your way of lower objects. Um, there's one big tree here somewhere. I don't see it right at the moment, but anyway. So there's landscapes you can put in Stellarium too, and I'll show you in a minute. I put in one for my home observing location, so I know when things are behind my neighbor's house or my house or what have you. Let's go back to, well, no, this is fine. We'll just go from here. Okay, so then another thing. So I want to make 2 points here. One is, this is kind of orientating, showing the sky for visual observers, right? So we can take the constellation lines away, we can put the constellation lines in, we can take the constellation labels away, you can label stars and deep space objects and all of that. So this is kind of a good visual approach. And then the other thing I talked about how this is a full-on planetarium, like you would go to a planetarium and see a show, is I also did some scripting with their scripting language, which is basically just JavaScript. So for instance, for last night's armchair star party, we got people oriented in the sky, pointed at Polaris, and then we said, well, what if we wanted to go look at M3? And so I run the script, and so this slide that came up here is actually part of the animation, and it's showing inside Stellarium, right? So we talked about M3, and here's the finder chart, blah blah blah. And then I can, when I'm ready, I can press a button and, it'll actually, put some text up. I've got it, it goes to the constellation, then it goes to the object, and then it zooms in. And, this again is a SJAA image, right? Take the stars away so that I can manually put them back here for a minute. So see, the stars are all lined up, but some of them bloat some of the stars in the image, so it's not super attractive. So take the stars away, and there's, PJ's beautiful image of M3, right? And then you can press a button and show another slide, talk about the image, whatever. Press a button and zoom out. Um, so it just, there's a ton of stuff you can do. There's a Messier marathon script that comes with it, and just all kinds of really cool things that you can do with the scripting language. So that's all I wanted to say about Stellarium for visual. So let's go ahead. Let's start moving now over towards the telescope. So. Just to get oriented here, first I want to look at my all sky camera. So let me get back on the YouTube over here. I don't know if this is going to show on the YouTube or not, but there's the Big Dipper right here in my all sky camera, and you can see it, pointing over to Polaris. So that gives you kind of an orientation, this way's north, and this palm tree is sort of southish. And the good news is the reason for the all sky camera is there's no clouds in the sky, just this big street light over here. Oh well. I can brighten this up a little bit. I think, yep, yeah, oh yeah, so you can probably see the Big Dipper better now. And there's some other light action going on. And so we'll see planes and stuff come across here. But this is up on my roof, and so I can see when there's clouds and stuff. Um, but let's go ahead and jump over to the telescope. Okay, so this is my telescope computer. And here we have Stellarium yet again, but it looks really different now, right? So, the constellations are gone, the constellation lines are gone, and now we've got this grid pattern here. What's going on with that? So, this is the right ascension, the RA and declination deck grid that's important when you're imaging and for finding things according to their coordinates. And then there's a couple other lines that are important to me. Um, I see M3 has gone across the meridian here. Hopefully, oh, I haven't slewed yet. Okay, that's all good. Uh, this line here from north to south through the zenith, through the highest point in the sky is the meridian. So I need to know about that when I do meridian flips. And I also need to know about this equator here uh, for the best calibration of the auto guiding software. You're supposed to do it within this square right here, sort of 1 hour of RA and 10 degrees of deck from the intersection of the meridian and the equator. So that's why those lines are there and why they're bright colors and whatnot. And then you can see, this is my neighbor's house, and my house is over here. We can turn the landscape up a little bit. So you can see that. Yeah. Okay. So I have a pretty good view, other than my neighbor's house being, like literally 6 feet away from my telescope. But what can you do? Um, so this is the stellarium, and you can see here this orange reticle is representing where my telescope is pointing, and that's because of this mount driver EQ mod talking to stellarium. So, what you can do with that is pick some object in the sky. So for instance, we can click on M3 or search for it and go to it, right? So my mount is unparked. It's not flashing that it's in park mode. And I'm probably going to hate myself for doing this, but just so we can have the fun of watching the mount move, I'm going to put this camera over here. It might mess with the audio a little bit, and it might not even work. Okay, that's not going to work, so we'll just get rid of that. But I do have a camera pointed at the telescope that sometimes works. All right, so what we do here is we say Control 1 for the first telescope, and you can see the telescope is moving, and I can hear it through my open office door moving, and it's going to come over here to M3. Okay, and we can do things like center on M3 and zoom in. And there's PJ's picture of M3 again. And you'll notice the telescope isn't pointed quite right, and that's just, again, the inaccuracies of everything, but we're going to fix that when we get a little deeper into this. Let me see my notes here. What I want to go to next is I usually sort of warm up the software before it all connects together. So the next thing I do is I go into the auto guiding software, and I see here that I've already connected connect the the guiding camera and the mount driver. So that's all good. And then we can actually start taking images through that guide camera. So that's what that looks like. And just to prove that we're going to be able to guide, well, actually, I can let it pick the best guide star. It likes that one. And one of the advantages of having a semi-permanent setup is, you don't have to recalibrate PhD2 every time. So this is calibration from, a week ago or so. And so we're already auto guiding, but we're not completely on the target yet. So that was just to prove that things were going to work right. So I'm going to stop that. Okay, and then let's go on to the last piece of software, which is Sequence Generator Pro. So a lot of stuff going on here. And there's a lot of little widgets. These tools around the edge are widgets, and you can arrange them differently and decide which ones are important to you. This is just the setup that I use. You got some histograms here and some statistics about the images as they come in. Here you can control the size of the image that you're looking at. I actually don't look too much at this section here, but this is supposed to be a high-level view of what's going on. And then over here we have a graph of the number of stars and that are detected and their quality of focus. And there's a widget here for the real-time focusing, which I'll show in a little bit. And then we have camera temperature. My camera temperature is currently minus 20 degrees, which is what I asked for. And it's using 69% of the available cooling power to get to that temperature. So that's all good. This is the focuser position and temperature and all the controls around the focuser. This is a graph that will show what PhD2 is doing in terms of how the quality of the guiding. And this widget is telling me which filter is in position. And then this one's at the bottom because I'm not currently using it. This used to tell me my local weather conditions. Unfortunately, Weather Underground stopped the API for that. So unless I write something myself, that's not working anymore, but that's not critical. So that's sort of the stuff around the outside. Um, then you have a control panel with tabs for each of your types of gear, the camera, the filter wheel, the focuser, the telescope, meaning the mount, plate solving, auto guiding, and miscellaneous other stuff, which in my case would be the rotator. Okay, and then this window here, which is always seems to be in the way of everything, is the sequencer. So this is where you plan out, here's my M3 and I want 3 events, a red, a green, and a blue, and for live stacking purposes, I'm just going to do 30-second exposures, but obviously you would do longer exposures, but um, I'm just going to take a bunch of them forever, basically. So that's where you do that. And then here is where you connect, just like in PhD2, where you connect the different pieces of equipment. My do-it-yourself rotator, the electronics are actually not on the telescope right now because I'm in the middle of moving them from being on the focuser to being on the telescope to have them be less in the way. So right now, if I want to rotate, I can use this manual rotator, which is that thing where, it tells me move it 5 degrees, and I run out and move it what I think are 5 degrees and run back in the house and do that thing. And then up here, you've got your mount and your focuser and your filter wheel and your camera. So that's where you connect that stuff. Okay, so one thing I wanted to, well, let's do this sort of semi-manually here. So let's get on our target first. So I'm right-clicking on my target and I'm going to say center on target. Center on target M3, yes. So what this is going to do is take a picture of the sky right where we're pointed. And then it's going to compare that picture of the sky where we're pointed to a database of pictures of the sky. And this is sort of mind-blowing. Figure out where in the sky we're pointed to a high degree of accuracy. Okay, and it's going to happen really fast if things work good. And if things don't, then there's a failover method. So here's this little plate solver piece that comes free with SGP from Planewave Instruments, and it's going to start, and it's done. That's how fast it is when it works. So now SGP knows where we were in the sky, and it's going to tell the mount and the planetarium, hey, you said you were pointed at M3, but you were actually off by 1,154 pixels in RA and 905 pixels in DEC. Get your act together, right? So the mount driver is going to update its model of the sky, repoint the telescope to where M3 should be, and then the process is going to repeat until the error is less than a user specified value, which in my case, I think is 50 pixels, if I remember. Oh, yeah, total error. Anyway, yeah, I think it's, oh, here it is down here, 50 pixels. Yeah, 50 pixels. But you can see that we're dead on M3 already, right? There's M3, a globular cluster. And in fact, yes, we have success. So that's plate solving. So that's the first thing. Now we're dead on target. And if I go back in here in Stellarium, and I can turn those stars off so you can see better. Yeah, see, we're right on uh, M3. Okay, so that's all good. And we're uh, tracking with the mount. We haven't started auto guiding yet, but well, actually we can do that now. Let's do that. So again, can start taking exposures with the auto guider. Gonna let it pick a star. I can brighten the display up a little bit. Okay. And by the way, the stars look funky in here on purpose because of that on-ag autofocus system, and that's a little more detail than I want to go into right now. But the funny shape of the star is actually caused by astigmatism, and it's there on purpose to figure out when it's in focus and when it's not. Let's leave it at that. So we'll start guiding and go back over here. And I want to demonstrate one more thing in SGP before we actually start sequencing. So again, normally I use this focus lock thing, but I just want to demonstrate what a SGP autofocus run looks like. So we're in the control panel here. We're going to go to focus, and we're going to see I have use autofocus unchecked, but I'm going to click run just to run it manually. So it's going to give me a graph here, and on the x-axis are positions of the focuser, and on the y-axis is the half flux radius, which is a measure of the quality of the focus, lower being better. And you can kind of relate this to the, 2 would be the 2 arc seconds. So if we get to 2 or below, we're getting good amateur quality seeing. So what this thing is doing is it pushed the focuser out away from where we were by a certain amount, and then it's going to walk it back in, taking an exposure at each step, and we should get a nice V curve, right? So it's out of focus, it's going to get better, 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 then worse, 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 and it's going to then plot a curve against that to predict, even if the best focus point was between a couple of between 2 step points, it's going to predict the absolute best position. looks like it's kind of waiting for the auto guider here to do something. So I think I'm gonna just stop this for the moment here and not worry about that. And I might have to restart the, let's, oh, there it goes. Okay. Well, yeah, it's confused because I stopped the auto guider. So we're going to cancel that and start over. All right, one more time. This is one aspect of something you want to consider in your imaging acquisition software stack is how well does it recover when something goes wrong? And of course, they all try to be bulletproof. And it's still waiting for the guider. I don't know why it's doing that. I have something in here that's telling it to use the auto guider. Well, I may have to bail on this part of the demo here. Have to try it with a brighter guide star here that I manually pick. I guess that bright one is too close to the edge. Try this one more time. We are live, folks. Some of the frustration of astrophotography. I think the other way to handle this would be to go in here and change our rules about auto guiding. I don't really have this selected, but let's just turn this up for a minute. Okay, run. One more time and then we'll move on. Okay, this is moving a little better now. So see, we're starting to get this V curve and we're going to start, the program will start plotting a curve against it here in a point or two more. Yeah, Rob, I'm looking at your notes in the chat and I figured you would set me straight here. Pause and auto guider during focus, yeah. So it looks like our scene is not as great as two arc seconds, but it's pretty good. Okay, so again, it's plotting this curve to figure out where the best point is. So it's actually going to repeat that process because it wasn't super happy with it. But anyway, that's the autofocus routine that's in SGP. So I just wanted to show that before I do my normal thing, which is because not everybody's going to have this ONAG stuff before I start this whole process. So um, connect all. So this is also looking at that, as I said, the shape of the guide star. And if you look over here at you probably can't see it because the font's too small, but this current position focuser is now starting to be adjusted by this real-time process. So that'll turn green and be in focus, and that'll just keep going the whole time we're imaging. So I'm not even going to wait for that like I normally would, but we can go ahead and just start the sequence now. So I'm just going to click on Run Sequence, and it's asking me if I want to start right now because normally you would have this target marked as slew to it and start, and I have it off right now because we manually got on the target ahead of time. So I'm saying yes, I want to image from here. So now now we're imaging, right? And again, I'm doing really short exposures because I'm going to be live stacking versus saving long exposures for later processing. So it changed the filter to red, and it's taking a 30-second exposure. It's about halfway done. And in a minute here, excuse me, it'll pop up the first exposure. So there you go. There's a Astroimage. That's a monochrome camera through a red filter of M3. So I've sort of demonstrated all of the various bits and pieces that you have to put together to get to this point. It's now um, again, as a option here for live stacking, I've got it set to rotate through the filter events versus take all the reds, then all the greens, then all the blues, just so that we can get bits that we need to make a color image faster. So now it's doing a green filter. That's the green filter. And now it's setting the filter to blue, and it'll do the blue filter. So the other thing I wanted to show then is the live stacking with Astro Toaster, not to be confused with Astro Tortilla, which is a plate solving program. So I'm cheating a little bit here because this is showing live stacking results from last night of these images that were taken last night during the Armchair Star Party. But just to continue that same session, monitor, stack, auto refresh, and this is the progress bar here. So what this is doing is it's watching the folder where those light uh, exposures are called lights, right? That we're taking of our data. It's watching the folder where those are going into, and every time it sees one, it stacks it in Deep Sky Stacker. And so you end up with a stack of reds, a stack of greens, and a stack of blue, and then it merges those stacks into this color image that you see here. So here's our color image of M3 from a monochrome camera with filters. And these bottom ones here are from tonight. You can see, well, you can't see, but I can see the date is the 24th right? So it's already created a red stack, and now it's working on the green stack and then the blue stack, etc. So that's if you were doing a virtual star party, a way to quickly get astro images up in color is live stacking with AstroToaster. And then there's other programs that will live stack, but they're typically just monochrome images from a given filter. Okay, Bruce, are you out there?
I am out here.
Okay. Are you in a
I do.
position to show some stuff?
I am.
Okay, awesome.
I'm poised to start a sequence.
Awesome.
Let me take your screen here,
Yeah.
and
So I should get my stuff
hopefully
out of
things
the
will
way
work
here.
out.
Yeah,
The
give me a second to get my stuff out of the way here because I need to see the meat, hangout meat, so we can see you. Okay.
it's already started to present me. Okay. So,
Uh,
can you see my Voyager screen now?
I can, yeah.
Let me move my camera. Okay, less bandwidth for the camera now. Okay, so this is Voyager. I have been using Sequence Generator Pro, like Glenn, for a couple of years, and I have a love-hate relationship with it. There are some things about it that I really love, and some things about it that it sometimes lets me down. It sometimes fails, and I got this software a while back when it was on sale before they raised the price, actually. And right now it goes for a little over $100. It's made by, as Glenn said earlier, a guy who is in Italy, and he's in banking finance programming. Uh, so he, like Glenn said, he can't fail, and his software is basically built around the core concept of the show must go on, don't stop unless it's absolutely necessary. And you know, I started setting it up about an hour and a half ago. I really actually, having used it in like 6 months, I took a look at it about 6 months ago, and you know, a lot of people are using it to good effect. I see some really nice images coming out that have been created using this software. One thing I like about it is that it interfaces with other software that I have. For instance, my mount is a software bisque mount. It came with a program called the SkyX Pro, and that actually always is running in the background whenever I'm running my Paramount MX Plus mount. And it acts as a driver for the mount. But more than that, it has built-in plate solving that's really excellent plate solving. It can handle cameras and filter wheels and stuff like that. And so Voyager actually interfaces with the camera part of the SkyX Pro and the plate solving of the SkyX Pro, and it also uses it for its sky maps, for its planetarium, they call it, software. So when it's looking for something, it looks it up in the database on SkyX, I believe, and it will plate solve to make sure that it's on target and rotated, and and then it actually also interfaces with the guiding software that I use, PhD, which is a free guiding software Glenn has talked about and shown you guys. And from what I can tell, having set it up over the past couple hours, it looks solid. The more I look at the interface, the more I like it. And this is kind of like jumping off a cliff. I did start a sequence and then stopped it. I didn't want it to actually go too far, but it looked, you know, there were a couple of hiccups that I had to figure out. but I was able to get it figured out within a couple hours, which says something about the software and the interface. So right now, all my gear is connected, as you can see here. The SkyX camera add-on, the mount, the PhD guiding, the planetarium part of the SkyX, the plate solving of the SkyX. The focuser that is going to be used is actually connected through the SkyX. It's a Nightcrawler focuser made by Moonlight. It's a really nice focuser. The autofocus routine that it's going to use is part of its software rather than rather than the one that's in the SkyX. It's going to use part of Voyager to do the autofocusing, and it has a few different ways of doing it in Voyager, which is pretty cool. I have a flat device called a flip flat that acts as a cap at the end of the telescope. It's automated, and this software can open it and close it, and it actually has a built-in light panel that it can light up at varying degrees of brightness so that you can do flat frames to calibrate and correct deficiencies in your optical train, whether it be a dust bunny, a dust speck, water spot, or something that makes a spot on your image. You can calibrate it out with flat frames. Glenn probably already went over that. It also makes up for the deficiency that you sometimes have called vignetting, where you have light drop off around the edges of your frame. And with this imaging train, I do have a little bit of that, so it's good to do flats. It also actually does, even finer. You would think that it would be kind of a gross, large issue that it would be taken care of when it's dust spots and things like that. But actually, it does more than that down on the sensor level, from what I understand, as far as the surface of the sensor and the way that the pixels are set up. It can actually help take care of deficiencies there too. So without further ado, let me see here. So this tab right here called On the Fly is where my sequence is set up. And they also have something called drag script, which I have not played with yet. Drag script allows you to somehow visually drag in different things. I guess maybe using these over here, you can somehow set up a script on the fly by putting different parts of your sequence in there. But tonight I'm going to do the on the fly part. I actually plate solved on an image that I had done before a couple nights ago. I'm going to be imaging Messier 101, which is also known as the Pinwheel Galaxy. So I basically opened it up, solved it. We can do that again, actually. Just hit solve, and it will solve it, and it will ask me if I want to use it to populate the target, and I'll say yes. I can go over here. I actually set up my sequence with this button. I have it set up to do red, green, and blue filters. It's going to do by slot, which means that it's going to actually do 3 of the reds, then 3 of the greens, then 3 of the blues, and then it's going to go back around and start over again. And it's going to do that 10 times. It is going to do 300 seconds for red and 120 seconds each for the green and blue. And let's see, what else can I tell you about this? Basically, that's it. There are a number of different options down here for guiding and stuff like that, and it will take care of that automatically, hopefully. So hit OK. I'm going to hit this to start the sequence and run. It's opening up the flip flat at the end of the telescope, and it's pausing guiding if it were going. It's slewing to the target. Checking to see if it needed a meridian flip. It's already past the meridian. Doesn't have to do that. the way it's set up for focus is it's going to slew to a star that's nearby and focus on that star and then slew back to the target. You can also do focus of a field of your image, basically your field of view. It can focus on the entire field of view.
I don't know what to do because it just says no data, but I'm sending data. Now it says excellent connection. We're back. Go ahead, Bruce.
Oh,
So
your audio is breaking up.
okay, we're back.
We're back?
We're back.
Okay, so it's just going through a focusing routine right now. Sorry about the dropout, everybody. With the pandemic, a lot of people are using the internet more than usual, I guess, even late.
Yeah, it's a long weekend, right? Sunday night, everyone's watching movies.
Okay, so it's progressing through the autofocus routine. It does a V curve, just like Glenn showed you in Sequence Generator Pro, and it is verifying that it got to focus. It actually got down to half flux diameter 1.87, which is pretty good. Earlier, when I was focusing, it was more like 3. So I thought the seeing actually wasn't as good, but maybe it's starting to improve. Okay, so now it's starting the guider. It's going to use PhD, which I'll bring up so you can see it. Here's PhD. It's actually calibrating. It lowers the exposure to 1 second for calibration and calibrates near the target on a guide star that it selects automatically. Usually I calibrate PhD myself, and I usually go to the southern part of the sky, to the celestial equator and meridian intersection, and I pick a star near and say that that's what but you can also calibrate near your target, and so that's what it's doing, and it does it. Should be done in a few seconds. It moves the telescope up and then you know, or north and south and east and west. And how far to move the scope in order to move the star a certain amount to keep it centered. All right. Now it's going south. It's almost done. And it's guiding now, I believe. Well, it should be. Let's see. I'm gonna clear this. Clear that. I guess it paused. It's not guiding yet, but it did the calibration, and it will start guiding when it's satisfied that it has plate solved and is back on exactly the right spot that it wants to be for my target.
This is a lot like
That goes, so it's
ACP.
going to start guiding now. It selected that star, or at least it looks like it did. Yes, it's guiding.
This is a lot like ACP,
Ah,
Bruce.
really? Okay.
Yeah.
It, it left it, yeah, I haven't really got any experience with ACP. It left it at 1 second of exposure, which is would not be my choice with this mount because it's not averaging the seeing. I'm going to try and manually increase that to maybe 4 seconds. And hopefully it won't be that I did that, and it won't cause any problems. It looks like we're actually exposing my first exposure of my sequence in the background there. And There. Okay, so now 4-second guiding. And the thing about that is because your star image is moving around because the atmosphere is kind of fluctuating and distorting the star image that you're seeing. So by doing a longer exposure, you're averaging the position of the star and getting a more accurate location of the reality of where the star is over time. And my mount is a decent mount, and it's generally tracking in the way that it's supposed to be tracking. So if you try and adjust all the time to where seeing is going by having a really short exposure, like 1 second, you're actually bouncing the mount all over the place, when in reality, the best thing to do is to keep the mount in the same spot for a while and see what the average is, rather than to go after where it looks like it is at any 1 second period of time. So they call that averaging out the seeing, averaging the seeing, and it's actually pretty good at a 4-second exposure. Looks like about a half.
Hey, Bruce, can you hear me?
0.47 arc seconds.
Can you hear me, Bruce?
Yes.
Uh,
Yes, I can.
I think your
Yes,
screen,
I can.
yeah, I think your screen is frozen for me, because we're just showing like you're about to click on the 4 seconds and the graph isn't moving. I think the only thing I can do about that is dump out of the meet and come back in. So let me try that. So we'll pause for a minute while I do that, or you could try that. You want to go
I
back in?
just, uh,
Yeah,
I
you stopped
just, can you
presenting.
hear me, Glenn?
Yeah, I can hear you. Go
Can you hear
ahead.
me?
Yeah,
Yep, Bruce, we can hear you.
Anybody?
Yeah,
go
we can hear
ahead
you.
and try
I
presenting again.
tried to stop presenting.
Uh-huh.
I'll try restarting presenting,
Perfect.
and we'll see what happens. Yes. Okay. How about now?
Hasn't started presenting yet.
Can you guys see me?
We
Can you
can,
see the screen?
uh, I
No,
cannot.
Huh.
not yet.
Okay, so can you hear me, Glenn?
I can hear you, yes.
Uh,
Let
okay,
me,
so it says, sorry, an error has occurred when screen sharing, and can't share my screen, so dismiss. So I'll dismiss it. I'll stop sharing. I'll try again. And
it looks like it's going to work.
okay, are you guys, are you seeing my screen now?
Now we see it, yeah.
Okay.
Excuse me.
I have a good Wi-Fi signal here, and
Yep, we can
it
see it.
should work. So I updated the guide exposures to 4 seconds, and I see in the monitor, it's kind of like a log, right? And you can see that it updated to 4,000 milliseconds as a guiding parameter change. So you can manually do that, and I would be surprised actually if there's not some place in here where you can tell it that you want to have longer exposures in general, um, and have it do that. So let's take a look at my sequence if I can. Here's the sequence.
We
Not sure
lost
how to
your
bring it up.
we lost your screen again,
There
Bruce.
you go.
Can you hear me,
Huh.
Bruce? Yeah. It's like you're
Yeah, I
not
can hear you.
presenting. Okay. It's like you're not
Um,
presenting.
well, I'm gonna reconnect to my remote here too, because that froze up for some reason.
Sounds like
Maybe I
an
should
extremely
try
local
reconnecting to the meet.
Yeah, you can try that. Extremely local network issue within your office there. Yeah, whatever you want to try,
Huh.
and we'll
Okay.
we'll try it once, and if that doesn't work, we'll call it a night. Any questions
Hmm.
while Bruce? I can put my camera up here.
No, there's just only one comment that the screen is really blurry, but it is moving.
Yeah, we that's a problem with uh, software that's designed for 1080p and then small fonts, and then you run it through compression and put it through YouTube, and
Yeah,
it makes it rough. Maybe we can think about some sort of screen magnifier mouse thing that would let us zoom in on stuff.
yeah,
Uh,
that's a great idea. And then
yeah,
for some of the folks that are on the feed that are still on the feed, you could try raising your quality on the YouTube as well.
yeah.
But I don't know if that will help.
That's one of the things that we talked about last night was setting your YouTube to dark mode and getting the highest quality that you can helps with the visibility. But yeah, I understand the fonts are really small in these Astro programs. Hey, Bruce, we can see you. I don't
Hey.
hear you. Oh, there you are.
Um, hey. So I use a firewall in Mac OS called Little Snitch, and I think it might have interrupted something here. So let me see if I can allow um,
It snitched
allow
on you,
incoming
huh?
connections via Chrome. Yeah, seems that way. Okay, well, maybe that'll do it. Okay, so let me try presenting. And let me try reconnecting this.
Hmm.
And that's nothing new. It usually only takes a half a second for that to clear. So, you know, I have been having some network issues. Um, Normally, I would be using a router that's out on our back patio. Basically, we keep it in a solarium, like a sunroom back there, and it just runs in that sunroom and hasn't been a problem until today. At which point, I think it got too hot. It's a little warm out today. It was a little warm out today, and that caused a problem. So anyway, here we are. Um, it looks like it's exposing. Let me see if I can go to the sequence. I don't know if it's going to let me view the sequence itself. I'm not positive how to get there. I can try this. Um, so that's the configuration for the sequence, but it doesn't actually show me the progress of the sequence. Um, this is new software to me. So this box down here, if you guys can see my cursor on the right, labeled sequence, start, remain, end. That's basically all the information that it gives me. What I can do, other than, I can see the scrolling, the log that's going by here with everything that's going on. But there is another part of Voyager called the Fit Viewer, and actually I already have it running back here. So let's take a look using their fits file viewer and see if I have something that we can look at that has come in through that sequence. Would be red images, I guess. Those are flats that I did earlier. Okay, so I have two reds. And there's my first image of M101, one single red. Could be sharper. I guess maybe the seeing isn't that great. It's 3.44 HFD.
Is that stretched in some way,
This
or?
is yeah. I think that it's an automatic screen stretch. I don't know how to turn off the screen stretch. Maybe it's the raw, show raw without any stretch. There we
Well, I
go.
guess,
Okay,
yeah,
so that's unstretched.
the top histogram is
And
unstretched and the bottom one is stretched then, I guess.
there you go. So this is a PixInsight nonlinear auto stretch. And I don't know why these two buttons, what the difference is. Low level nonlinear PixInsight auto stretch. So anyway,
Cool.
not bad, not
Yeah.
bad. There's a little bit of vignetting in the corners, as I mentioned. I have a little bit of vignetting in this image train, but it'll correct out with flats, and I'm on my way to a good image, I think.
Awesome.
Uh,
Anything else we need to cover?
yeah. Um, well, I think that basically covers it. It's doing everything the way it should. It's and it monitors my guiding. Let's take a look at the guiding. See how it is. It's really not bad. zero point 0.8 arc seconds RMS. Uh, maybe I could get a little bit better focus with the autofocus. I do have an on-ag in there. I need to tweak the settings in the on-ag a little bit and decided not to use it tonight. But it is guiding through that. And one of the nice things about the on-ag, aside from using focus lock for consistent focus all the time, actually is it's using a cold mirror, I believe they call it, and it's splitting the visible light off and sending that to the imaging camera that's on the side of it. And the light that is remaining is the near infrared light, and that goes through the mirror and to the guide camera that's on the back end of the telescope. And the near infrared light from stars is generally less affected by the seeing. So it should be a more accurate assessment of where the star is, at any given time, which makes it's basically correcting more for the fluctuations of the mount itself because of the gearing and the worm gear of the mount having little bumps and irregularities in it that causes the mount to not be completely perfect for tracking. So our guiding is really essentially the guiding is there to take care of the inaccuracies of your mount. If your mount is perfectly accurate, you really don't need much guiding, if any. Having more accurate position on the stars is helpful because you're not making corrections that aren't real. I think that basically covers it. I'm really impressed with Voyager so far. So we'll see how it goes.
Okay, great. And we seem to be having network errors on my side popping in and out. At least this
Mm.
YouTube is complaining about the stream. So this is probably a good time to call it. I think we've covered all the material I wanted to cover tonight, and thanks to Bruce for helping out and doing a demo and taking a risk on demoing something that he's not super familiar with. I appreciate that. And thanks to Rashi also for helping out with the YouTube stream, keeping an eye on that. And let me just go back to my PowerPoint here for the outro. Um, yeah, so we've got maybe 5 minutes, and if anybody has any questions, and if not, I'll go to the final slide. So we'll pause here for a second for the YouTube delay. If you've got any questions, this would be the time to type them into the chat window. And after I'm gonna, well, I guess if there's no questions, there's no reason to leave the chat open. But you know, you can put comments in the YouTube later if you're watching this not in real time or otherwise. We'd like your feedback. This is the first time for this slide deck, and you know, I'd like to keep improving it. So your feedback is more than welcome. I guess we don't have any questions at this point, so let me just go to the final slide. Thanks for watching. Again, um, you know, we've got a couple YouTube channels there. We've got the SJAA Imaging SIG program, the special interest group that Bruce runs, and we've got the meetup there as well. So those are QR codes you can point your smartphone at or copy down the URLs. So yeah, so thanks for watching, and we'll see you next month with either something similar or maybe we'll be out at Little Uvis. We'll have to see what happens with the whole COVID-19 thing. So thanks, and we'll see you next month.
Thank you, Glenn. Thank you, Bruce.
Yeah, we're out.
Thank you. Have a good night, guys.
Yep.